So I'll go ahead and introduce Shreyas. I've talked a lot about his work to many of you at this point, so I think that we're all very eager to see his presentation. So Shreyas did his PhD at University of Michigan, and then now is a postdoc at Stanford, and then will be looking for faculty positions from there. And he's done a lot of work in terms of like trying to make reachability and safety guarantees more scalable for doing real-time decision-making and planning while maintaining safety. And he has some really impressive results in terms of being able to have everything from like ground vehicles to quadcopters to manipulators, all planning in like a safe and dynamic way. And so he also has this really beautiful tutorial that I've referenced a few times that kind of gives a nice introduction to how these methods work. So today I think he's going to talk a little bit about this and the approaches for doing that computation, as well as the resources available. So with that, take it away, Shreyas.
Thanks for the really nice intro. Wow, that's very kind. Hopefully everybody can see me, and then I've got this subtitle thing working. We'll see how well it does with controls engineering lingo. So this talk will be about reachability-based trajectory design, and I'm just going to get right into it. So the kinds of things at a high level that I care about robots being able to do is navigate these complex scenarios where you may be interacting with humans or taking over jobs that are dangerous or difficult for humans to do. However, to really accept these things into society, we need them to be safe. So we want to make formal guarantees about what they're going to do before we put them out into the field. However, that can often lead to conservatism. And so the whole game in the motion planning world, as far as I'm concerned, is balancing safety and conservatism while still getting these robots to do stuff. RTD in particular is a technique that has grown out of a bunch of reachability analysis methods, which I'll discuss what those are. But you can apply it, at least what I'll talk about are wheeled robots, quadrotors, and then manipulators most recently. And the techniques that we use to make this possible are kind of split between whether they do things for safety guarantees or whether we're trying to do real-time planning. And I'll also explain why the real-time aspect is important in a bit. On the safety guarantee side, we spent a lot of time at Michigan thinking about how to model these systems and then learning about different reachability analysis techniques that make it so you can make strong guarantees. On the real-time planning side, and I'll talk a little bit about this, I've spent a lot of time figuring out how to represent obstacles in a discretized way, or in general, in ways that make it tractable to do, to solve non-convex, nonlinear optimization programs really fast. And we've also figured out ways to make it parallelizable. I'd say for today, what we're going to focus on is the sums of squares reachability that we've applied to wheeled robots, and then Zonotope reachability applied to drones. And just on this slide, I'll reference dissertation chapters in case you're curious, because I think it's quite a gentle but deep introduction to all of these techniques. Time permitting, hopefully we can get into the fetch robot manipulator stuff. And I've given Sylvia all my slides, or Professor Herbert all my slides, so that you can all reference it afterwards if you need. So before we dive into anything, I'll just show you a little video. Here we have this robot's own view of the world in the top left. We have a camera on the robot in the bottom left. We set up this little mock road and tossed some obstacles around. And then we give the robot a waypoint in a receding horizon way. It sees these obstacles detected with a LiDAR in red. It sees itself as a blue rectangle, and then it's computing this green blob, this reachable set, over and over and over at runtime. So what it looks like is basically what we hope to see is that the robot can do stuff autonomously and not crash. And I'll now explain what's going on behind or under the hood of that process. Before I continue, just feel free to interrupt with questions at any time. Just unmute yourselves. That'll be the easiest for me. And yeah, okay. All right, so first, some background. I'll try and relate this to what you already have seen. Full disclosure, I just converted these slides from Michigan colors to Stanford colors, hence the left side of the road is now suddenly blue. So just ignore whatever conventions you know about driving. All you care about right now is safety. To make a robot drive safely, we typically set up a receding horizon planning framework where the robot will be trying to get down the road, perhaps to this golden star goal position. Of course, there's stuff in the way, and the robot's sensing capabilities are not perfect, they are limited. So we adopt a receding horizon strategy, wherein we set up a waypoint, something intermediate between where the robot is and where it needs to go, plan a short trajectory using ideally a simplified planning model that is really fast for computation. And then the robot does what it wants to do to track that trajectory, which may not be perfect. Often we can describe the motion of the robot with what we call a high fidelity model. And you'll notice that both of these models are written as ordinary differential equations. That's the way I'll be talking about modeling a robot throughout this talk. But I can relate this to other types of models you may have seen in the literature later on. Anyways, by repeating this process of setting up a waypoint, planning a trajectory, and tracking it, ideally we can eventually get our robot to the goal. Of course, our models are never perfect, so we'll always have some error between what we wanted the robot to do and what it actually did. The challenges then are to plan with respect to this error, so to hold on to it in some meaningful way that's actually computationally tractable, to consider the fact that, yes, we discretize on the computer, but the world isn't discretized in the same way. So we need to consider continuous space and time to make strict guarantees. And then we need to do this really fast. So how do we represent the world around the robot to make it so it can make these decisions really quickly? Often one way to solve this is to set up, and I'll call this an infinite dimensional problem, but I'll explain what that means in a minute. Imagine that we just have this space of control inputs and the state space for the robot, and we want to minimize over the trajectory of the robot here, and hopefully you can see my mouse. Maybe, wait, can you see my mouse? Okay, anyways, yes. I'll just keep talking. Thanks. So we want to minimize over the trajectory of the robot and its control inputs for perhaps for all time, some arbitrary cost, subject to the fact that we have a high fidelity model, and we don't want that model to intersect with obstacles in its position or workspace coordinates. So an optimal solution may do some wiggly thing in the control space, and it'll produce some good trajectory in the state space. Unfortunately, we actually have to enforce these constraints for an infinite number of points in all the obstacles and an infinite number of times. So it is an infinite dimensional program because the size of the decision variable space is infinitely large. You can never put this on a computer, but you can always represent a finite dimensional problem on a computer. In the RTD case, we've taken a particular tack that lets us get to that finite dimensional computational representation. The first thing we do is we minimize over what I'll call trajectory parameters, and I'll illustrate what those are shortly. So this is drawn from a finite dimensional space, and the cost is translated into this finite dimensional variable. We then represent obstacles in this space, and then we decide what trajectories to choose over this, the complement of this unsafe set, let's say. We also choose a finite amount of time. And in fact, we represent the entire interval, not just discrete points in the interval. So we're still, in some sense, solving an infinite problem, but we're very clever about how we represent it. Hopefully, this problem looks a little bit simpler to solve. And if you're not familiar with this type of optimization notation, don't worry, you'll see lots of it, and I can explain it in more detail as we go. A solution to this problem might look like this. And then we'll solve this little problem that you see down here over and over and over as the car or robot in general is moving through the world. It's a receding horizon formulation. And then the trick to getting this unsafe set is to use reachability analysis over and over and over. Now, to ground this in a broader context, let me talk about where RTD fits in the scope of other methods. Typically, for making a robot move through the world, we look at a high-level planner that ignores the dynamics of the robot and generates those waypoints that you saw. This hands its output to a trajectory planner that tries to compute some short trajectory to achieve a goal. And finally, a tracking controller tries its best to track that trajectory perfectly. At the high level, you may be familiar with rapidly exploring random trees or A*, prototypical high-level planning algorithms that will spit out waypoints really fast, but they pay a trade-off the more complex you try and model the dynamics in these types of planners. On the other hand, at the lowest level, well, here we go. I'm skipping a couple slides. Okay. At the lowest level, you may see things like control barrier functions or model predictive control. And I believe Jason Choi gave a talk about CBFs. I'll point out in cartoon form how this works. But the idea of this is, given a trajectory, how do I track it as well as possible? And mostly this cartoon is just to give you guys a short illustration of fast track, which I think is super cool. So imagine I have my car and it's allowed to do whatever it wants in the world. And I just have to track that decision as well as I can. If I can compute a reachable set of the tracking error, then at runtime, I can use that reachable set to essentially dilate obstacles. And so no matter what my plan for my car does, as long as it lives outside of these dilated obstacles, I know my car will not crash despite tracking error. So this is the type of object you can get from Hamilton-Jacobi reachability. So a similar technique is to apply control barrier functions. Often what you'll see is a nominal trajectory. In this case, let's say we're driving in a straight line, and that corresponds to some nominal control input shown on the left. When an obstacle appears, we want to construct constraints on the space of control inputs, and then solve a quadratic program that minimally corrects our control input. So we want to be as close to what we were trying to do while still being safe. However, it can be quite conservative to take this type of approach, because what it's doing is it's treating all higher level planners as a disturbance to the system. So that can be quite conservative. And hopefully you all have heard a little bit about this and have thought of ways to combat that conservatism. A bonus challenge specifically for CBFs is we don't know if that quadratic program is always feasible. Sometimes it is, and it's really cool. There's a work from Sam Coogan at Georgia Tech that recently shows how to ensure that that program is feasible. So it's not a problem that's unsolved, but sometimes it is. It's something to be cautious of. To summarize this sort of literature review, RTD fits in right in the middle here. It's a trajectory planner that balances the model fidelity that would make high-level planning intractable and the conservatism that you can see with certain types of low-level tracking controllers by enforcing safety at this trajectory planner level. And at the end of the talk, I'll discuss why that's good and why that's bad. Before I proceed, are there any questions? All right. So I'll now give a cartoon overview of what's going on, and then we'll get into some math in a little bit. Remember that I said we use these trajectory parameter objects. What they look like are essentially points in this parameter space in the bottom, corresponding to short trajectories in the robot's workspace on the top. If we look at this continuum of all possible trajectory parameters, it corresponds to this forward reachable set in the workspace, which is what I'll call the FRS. And the goal of RTD is to compute that object offline and then use it at runtime over and over. So online, we can intersect the workspace forward reachable set with obstacles and thereby identify unsafe choices of trajectory parameters. Then given a cost function, such as reaching a waypoint in the workspace, shown as this gradient of cost in the parameter space, we can decide over the trajectory parameters, basically solve that optimization program you saw earlier, and thereby find a short trajectory that tries to reach our goal, our intermediate waypoint. What we'll do then is actually track that, and despite tracking error, we know that this little green subset of our whole reachable set will lie outside of obstacles, and therefore our little robot will lie outside of obstacles as well. We can rinse and repeat this procedure, and here the edges of the slide themselves are obstacles. But we're basically doing the exact same thing, and a priori we specify that we'll repeat this procedure every t plan seconds. So up until now, we've always chosen this amount of time, and usually it's something like half a second or a third of a second. So it's a lot slower than a tracking controller running at 100 Hertz, but it's a lot faster than potentially solving for the reachable set itself, which takes often hours to compute. As I said, we'll keep repeating this procedure, constructing constraints and a cost function, optimizing, and then tracking the resulting trajectory. Now I'll point out what you haven't seen here is that in practice, we actually have to predict where the robot is going to be for the next plan. So there's some benefit to picking a very short duration T plan, because that prediction can be inaccurate over very long time horizons. Over very short time horizons, we find that it's actually pretty accurate because we have a high fidelity model of the robot.
And in practice, you use about half a second for that?
Yep. Yeah, half a second has been for basically every demo that I'll show here. The nice part is because we're using a parameterized trajectory space, we can construct a pretty accurate high fidelity model because we sort of know everything the planner might do. So constructing a high fidelity model isn't a huge challenge. And then constructing a tracking controller, again, because we know what the trajectories look like, isn't a huge challenge. I mean, it's not trivial, but it certainly makes it a little easier.
So the key thing here is restricting the planning ability so that you can have more knowledge about what it might do.
Exactly. And by making that restriction, you're losing something in flexibility, but you're gaining something in being able to say what the system's going to do and thereby make some sort of guarantee.
Are you going to talk about moving obstacles, your stuff on moving obstacles later?
Mm-hmm. I don't have much about it in this talk. I'll just point out how we handle them, but I can discuss it in more detail if anybody has questions when we get there.
I have a question.
Yeah, go for it.
I would like to know in the 3-layer of architecture, you are choosing different trajectory parameter. Do you also change the parameters in the control or change the different control law?
So in all the work so far, we fixed the controller a priori, and usually it is parameterized in some way. So having control gains or some other parameterization. We haven't explored, for example, adaptive control, but there is sort of upcoming work, at least from my friends at Michigan, who are exploring how to incorporate some types of model uncertainty, which could appear as for example, controller uncertainty, in which case you'd be selecting from potentially a family of controllers. So the way I guess I'm viewing your question, and hopefully I haven't misunderstood, but it's, do we adapt the controller to potentially uncertain models at runtime? And we're working on it. We haven't yet, but we are working on it. Does that answer your question?
Yeah, perfect. Yeah, another question is, do we also always choose like trajectory parameter space like much lower than the high fidelity model? I think so, right?
Yeah, basically the idea is to make it computationally tractable. However, in the case of the manipulator, if I have time for it, I'll show you some videos, but we still have to deal with the fact that we're trying to control all of the joints. So you're kind of stuck with a high dimensional space, in which case the simplifications we can make are to use a kinematic model instead of a dynamic model, and then to decompose the reachable set and compute one for each joint of the manipulator. But that's a good question. And in general, yes, we choose a lower dimensional simplified planning model.
Okay, thank you.
Good questions.
I had a quick question about, so for the half-second duration that you plan for, if anything unexpected pops up, then do you expect your lower level controller to handle it, or how do you deal with that?
That's a good question. We prove bounds on the sensing radius required. So we make an assumption about how well we can sense the world around us, and we prove the some minimum bound of, hey, I have to sense everything within this distance to some accuracy. So usually just a conservative representation of static and dynamic obstacles. That way, nothing unexpected pops up in that half-second window. All right, quick interlude. What's a reachable set anyways? And hopefully this will give you a different flavor from what you may have seen in the class. Consider a system described by a differential equation, an ordinary differential equation, and some target or initial condition set. The set of all conditions, initial conditions that reach this set at time t is what we usually call a backwards reachable set. So if I flow the system forward from any point in here, I'll end up in this target set. If I start in this set, then after t seconds, I'll end up in this forward reachable set on the right. So this is the super high level generic description that hopefully you've seen and that I'll be using through the talk. I won't be talking about backwards reachable sets very much. And indeed, I'll just focus on, oh, this should say FRS, so raw and untested slides. Anyways, a forward reachable set can be written as the set of points that are reached at time t, started out in our initial condition set, and obeyed the dynamics for the entire time horizon. We will also consider reachable tubes. And in fact, all of the things that I'm calling reachable sets in this talk are actually reachable tubes. I haven't made the distinction between tubes and sets in my work, but if you're more familiar with the tube lingo, then think of all of the objects I talk about as reachable tubes. Okay. I'll talk about wheeled robots, and I also point out none of this is solo work. All of these things have been put together by a lot of people working over many years. So I'll show their faces and names as we go. In the wheeled robot case, I'll discuss how we parameterize trajectories, how we compute the forward reachable set offline, and then how we represent obstacles online. And that's where I'll answer the dynamic obstacles question. For notation, just as a reminder, our high fidelity model, our accurate description of the car, has time in this interval, high fidelity states and inputs. And then our simplified planning model has a lower dimensional state space x and trajectory parameters k. We describe our parameterized trajectories with this little f, and our high fidelity model trajectories with this f high. So hopefully the notation will be very clear, and you should have the PDF of these slides to reference later as well. Our trajectory parameterization, we found that just computing these Dubin's path like arcs is pretty much always going to work for cars because they're pretty short. In fact, what we do is we parameterize a speed and yaw rate profile that travel at a constant for some time and then break down to 0 at this final time in each plan. So T plan is where we've traveled at some or commanded some constant speed in our low dimensional model, and then we rely on our high fidelity model and tracking controller to track that behavior. By incorporating this type of braking maneuver in every single trajectory, no matter what we're doing, we always have a braking maneuver available as we stitch these short trajectories together over and over through time. The reachable set then is given a trajectory of the planning model and whatever our high fidelity model may do, a blob surrounding that planning model trajectory that incorporates the behavior of the whole vehicle. We represent this as an additional G function, which is representing the tracking error, and it's multiplied by a disturbance D. So these two things together are what I call the tracking error model. And the disturbance in particular just goes from time to -1 to 1. So the idea is, if you can hold on to the tracking error conservatively, then you can solve basically this differential equation in a clever way and hold on to all possible trajectories despite tracking error. So assuming this G function upper bounds the possible tracking error, you can choose that disturbance to basically drive the planning model trajectory, the simplified trajectory, to exactly match any of the high fidelity model trajectories in the states that you care about, so that lower dimensional state space. Okay. Now, how do we actually hold on to this object on the computer? Consider again our simplified model, and this G function may look like this. This is taken from a bunch of traces of that rover robot you saw at the beginning of the talk. And then we fit G to upper bound all of the tracking errors. The forward reachable set is computed as the continuum of trajectory parameters and this blob in the robot's lower dimensional planning space using a sums of squares program and representing this blue forward reachable set object as a polynomial W. In particular, we can show that given a point in workspace and in the parameter space, so in this higher dimensional forward reachable set, the polynomial is greater than or equal to 1 on that point. So what you can think of then is to test if I'm inside or outside the reachable set, I can just evaluate a polynomial and check if it's greater than or equal to 1. So how do we compute that polynomial? Here's where sums of squares reachability analysis is the particular tool that we use and that you can see in the RTD tutorial and the RTD repository for the segue and the rover. To compute the reachable set, we begin by setting up an optimization program where we're trying to optimize over these 3 polynomials, and we're trying to minimize the volume of W. So the integral over the states and parameters of whatever W is. If we were to take W out to be a polynomial of infinite degree, then it would converge to an indicator function just on the FRS. So 1 on the FRS and 0 everywhere else. We add constraints to enforce the dynamics. So this V object here is basically acting as a Lyapunov function. It'll be negative and decreasing along trajectories. And then we add this Q function to incorporate the fact that we're computing the reachable set for a lower dimensional model, but we still need that tracking error to incorporate the motion of the high fidelity model. So this Q polynomial evolves along the trajectories of the tracking error, thereby incorporating our disturbance function D. Finally, we have some constraints that tell us that W is greater than or equal to 1 on the FRS. So if this formulation in the green box doesn't strike you as obvious, that's okay. It took me years to figure that one out. But the theorem that you can basically do some algebra on these constraints and show is that if a point is in the FRS, then W is greater than or equal to 1. Now, the reason that this is sums of squares reachability is because we have to represent these non-negativity constraints somehow. And in particular, we do this using sums of squares polynomials. So interlude number 2. What's a sums of squares polynomial anyways? And it's going to look often something like this paraboloid in the bottom right. Before I dive into this, are there any questions? Okay. Suppose we have some point in Rn and some arbitrary monomials. So here I've written the monomials as a function as a function m, where I plug in x, then it's just some basically polynomials with only one term in the variables of x, or in the coordinates of x, let's say. Suppose I have a matrix Q, a square matrix that's positive semi-definite. And if you're not familiar with what that means, I don't have a definition like in the slides for you, but you can, well, I'll leave the specific definition for later, but you can think of it via the example on the next slide. That will be probably the easiest way to understand it. If I write down a polynomial P, which is written as this M, Q, M transpose object, so you can think of this as the dot product of M, these monomials with themselves, and multiplied through by Q. So this is a generic quadratic form. Then what we've done is we've summed the squares of all the monomials with some coefficients. And as long as the coefficients are chosen carefully, which is equivalent to Q being positive semi-definite, then we know that the polynomial P is positive everywhere. So it takes an n-dimensional number and spits out a positive real number. Therefore, if we can find a sums of squares polynomial, then we can say that it's positive on the sets that we care about. In particular, consider a semi-algebraic set defined by a polynomial h. So the set h is all the points where little h is greater than or equal to 0, and it may look like some blob like this. Suppose I have some other polynomial p, and I can write it as a sums of squares polynomial plus a sums of squares polynomial times h. Then p is positive on this set h. So what I've done is I've taken an arbitrary set in Euclidean space, and I can define that set usually with a positive polynomial. That's something you can do a priori. Then you can find a new polynomial that's positive on that set. This is really useful because if I want to find something that's like a Lyapunov function, so negative and decreasing, then I can enforce this type of sums of squares constraint. I can search for this formulation by saying that the Lyapunov function and its derivative are negative on the set of all states of my system. And to be clear, this is a conservative condition. So if these are the contours of P, then the set P, or the set defined by the zero superlevel set of P, is certainly positive on the semi-algebraic set, but maybe also positive elsewhere. Okay, so that was a lot of math to throw at you, but the big takeaways here are sums of squares on a set is equivalent to non-negativity on that set. And to check if something is sums of squares means to find that positive semi-definite Q matrix that I mentioned earlier. Critically, finding such a matrix can be done with semi-definite convex programming. So it'll take a lot of memory because you're representing really large matrices, but it's convex, so it comes with optimality guarantees. In other words, this is the root of proving that we will find a polynomial that's greater than or equal to 1 on the reachable set. That is to say, by representing everything with sums of squares polynomials, we can actually prove that this property holds. Any questions?
Are you going to talk about when using sums of squares is a good idea versus when it would be maybe frustrating?
Not in huge detail. I have some answers to your specific questions at the end of the talk, but in general, you're going to have a really hard time finding sums of squares polynomials in high dimensional spaces. If you recall, we have this vector of monomials. Oh, okay. Nope. Sorry. All right, this vector of monomials. Often we'll try and hold on to all monomials up to a certain degree. So like every single permutation of each of these variables up to maybe degree 2 or degree 8. The size of this vector blows up exponentially with both the dimension of the underlying Euclidean space and with the degree that you're choosing. So what that means is that the size of this matrix Q, which is the size of this vector squared, blows up exponentially squared as you increase the state space dimension and the degree of the sums of squares polynomials that you care about.
So about how high dimensional do you usually, can you usually do, in a straightforward way? Because I think it's still more scalable than some of the standard HJ reachability stuff. Is that true?
It can be. So we've gotten up to 5 dimensions. Annoyingly enough, time is always an additional dimension that you lose when you're representing these things. So it's 4 dimensions plus time for all the wheeled robot stuff.
Okay, okay, it's pretty similar.
2 workspace dimensions, 2 trajectory parameter dimensions, and time.
Thanks.
Yeah. The tricky part then is to be more clever about scaling it up. There's ways to do it with exploiting sparsity, so sparse sums of squares optimization. The problem is then the reachable set becomes much more conservative. So you end up with like lower degree or less expressive shapes. Okay. So instead of a shape like the wibbly wobbly H thing that we saw earlier, you'll just get paraboloids or ellipsoids. Right. And so that's the trade-off you pay with these polynomials. And that's also why I haven't used them in a couple of years, because I thought zonotopes are cooler. And we'll talk about zonotopes in a bit. Cool. Oh, Zootopia is apparently the subtitle for Zonotope. That's great.
Quick question. So you're saying that if the degree of polynomial is bigger, the rate of convergence is bigger too? Like how is it different in terms of rate of convergence?
Off the top of my head, I don't know. But in general, the semi-definite program that you set up is going to run much slower. That speed is because you're trying to hold on to a really large square matrix in memory, and you're holding on to just more stuff. So it's going to go slower. I don't know what the rate is in terms of like the rate of convergence as a function of the dimension or the degree. My understanding is it's exponential or close to exponential, which is unfortunate. And in practice, that's what I've seen as well. These things tend to blow up in how long it takes to solve. Okay, but that's a good question, and I'll do a little bit of reading later and see if I have a better answer for you. Okay, so suppose that we have this polynomial. Now, how do we use it? And I hinted at this earlier, where evaluating the polynomial greater than or equal to 1 tells us if we're inside or outside the reachable set. So what we really want to do is evaluate this polynomial on all of the points in an obstacle, and then that should show us all of the possible unsafe choices of trajectory parameter. In other words, then we want to construct this k unsafe so that we can optimize over our arbitrary cost subject to some constraint of being safe. Unfortunately, checking this constraint means that we have to evaluate that polynomial for every single point in the obstacle, which has infinitely many points. So all of a sudden we have an infinite dimensional problem to solve again, and we don't want to do that. However, using a bit of geometry, we can wrap this obstacle in a provably finite number of points by finding two tunable parameters. So R, a distance between these points, and then B, a distance away from the obstacle. The idea being that if I tried to squeeze my robot between those points, it could never squeeze between any two of them far enough to poke the obstacle. So we prove that such a spacing exists for arbitrary polygonal obstacles, and that they're bounded when my robot is convex and compact. The reason this is useful is because if I know I have a finite number of points equivalent in some sense to my obstacle, then I can say, if I evaluate my forward reachable set polynomial and it's less than 1 on all of the points in the discretized obstacle, then I've chosen a safe trajectory parameter. So what I've done is I've taken an infinite number of points and turned it into a finite number of points. And I can actually evaluate safety by evaluating a polynomial a finite number of times, which is super duper fast. So it might look something like this. When I evaluate W on all of these points, it'll be a bunch of little blobs that provably cover the unsafe set. If I then choose a safe trajectory parameter, I know it avoids collision with all of these points, so it avoids collision with the obstacle. Now, this is this is just inequality here, not less than or equals. So in practice, we pick some small epsilon to enforce this constraint. But wait, dynamic obstacles work too in the same way. Suppose I'm given a prediction of a dynamic obstacle. And here I'll point out, and hopefully you've noticed, I have not talked about perception at all through this talk. This is purely how do I plan once I know about the world. So if someone gives me a prediction of what another robot or vehicle is going to do, we can still find this unsafe set by discretizing in space and in time. So we prove that there's some time discretization and then spacing between the points. And you'll notice that the points show up inside of this blob as well, because if we start out with the prediction of a robot on top of our robot, then we need to know that we can go out of it. So discretizing just the boundary is not sufficient, because that's like getting caught in a lasso, which happened to our robot in simulation a lot, and we were really confused. If I map all of these points through that W polynomial to the parameter space, I'll get all of these blobs covering my unsafe set. And then I can again optimize over just the safe set. And hopefully, if I do that fast, well, not hopefully, provably, if I do that fast enough, then my robot won't crash. All right, so what does it look like? Here's a car driving around with just random static obstacles on a 1 kilometer test loop up to 35 miles per hour, which is the speed limit of the test loop. So we didn't pick that for any particular reason. It autonomously decides to make these lane change maneuvers around the boxes. And it slows down for corners because it knows it can't actually make the corner if it's going too fast, because the reachable set won't fit inside the road boundaries that we also show as discretized obstacles. Since I don't expect you to believe every simulation you see, here's the top-down view of our Segway robot at the University of Michigan, and it's going to dodge these dynamic obstacles. Unfortunately, in this case, what we did is the obstacles don't react to the Segway at all, which turns them into really, really mean obstacles. It's like if you were walking towards somebody and they just walked right into you. So these scenarios all became really, really hard for the Segway to solve above 2 obstacles. However, over many such scenarios, importantly, the Segway never caused a collision. It would always come to a safe stop, and then somebody else may come run into it. So we started discussing a notion of fault in a collision in the dynamic case. Things get a little muddy once you start talking about the possibility that other robots may come run into you, or other agents may come run into you. And then finally, so I actually sat in the car at the University of Sydney, and this is with RTD running on my laptop and automatically navigating between these big, heavy concrete planters that would be very painful and expensive if we crashed into them. The idea being, yes, it actually worked on a real robot with me sitting in it. And that was a scary thing to sit in, but now we know. Okay, so that covers at a high level, that gives you a flavor for how this works on the wheeled robot side. And I have a link to the tutorial, which goes into much more detail about all of this, but still in a gentle way. I'll now discuss aerial robots, quadrotor drones in particular, to introduce a different way of computing that reachable set. Before I proceed, are there any questions on the wheeled robot side? All right. In the drone case, we use the following high fidelity model. We consider a three-dimensional workspace, and we look at the robot's position, velocity, angular velocity, and then R is a rotation matrix describing the attitude of the robot. One way to write down the dynamics here are as, maybe this doesn't look like it, but these are standard 3D rigid body dynamics for, in this case, a point mass with inertia evolving in space. The control inputs to the robot are the thrust, tau, and the body moment, mu. And in general, planning with this model in real time is hard. However, some of you may be familiar with the differential flatness property of a quadrotor, where you can plan with a much simpler model and then track that much simpler model with all of the states that you see here on the left. That model in particular, we simplify by using these trajectory parameters. So each point in the space, again, is a single plan in the workspace on the right. And we still denote these plans with the dynamics little f. Here, we're going from time and parameters to just the workspace. So R3, in this case, we specify the velocities of the center of mass of the robot, which is a lot less to specify than the velocities, angular velocities, and attitude matrices. So what you can think of this as is my simplified planning model specifies the velocities as a function of time and the parameters. And in particular, we construct these as polynomials that are piecewise varying in time. So these coefficients are time varying as well. But the nice part is then I have decoupled planning dynamics because I'm just looking at a separate polynomial in the X, Y, and Z dimensions of my robot. This means I can actually compute a reachable set without having to compute the reachable set directly of the high dimensional model. To give you a feel for what this parameterization looks like, let's look at just one trajectory. In particular, we have a 9-dimensional parameter space where our parameters are the initial velocity, the initial acceleration, and then a desired velocity at a time t desired along each trajectory. As before, every single trajectory ends with a stop so that as we're finding these online, if for some reason we can't find a new one in time, we can continue our previous one and come safely to a stop. The challenge is, well, the first challenge you'll see is that this is a 9-dimensional space plus 3 dimensions plus time, but we can make use of that separability property where we're computing it separately for the 3 spatial dimensions to compute smaller reachable sets and stitch them together.
Can I ask a quick question?
Yeah.
So for the previous slide, the trajectory parameters that you chose, like for someone who has some model and they would like to have this trajectory space, like how did you go about choosing these as being the trajectory parameters? Is it just kind of intuition based, or how would you go about doing it if you had some model that you wanted to control?
Over the course of, I would say experience based. So if it is intuition, then it's an intuition we built. We found that tracking error is proportional to the initial velocity and then the commanded change in velocity. And by including the initial acceleration, as opposed to saying I have any possible initial acceleration, then my tracking error is much lower. So the experience side was noticing, the first thing I tried to do was say, okay, all I care about is my initial condition, so initial velocity, and then a final position, which seems like a nice thing for a drone. The problem is when you compute those polynomials for which there's an analytic expression to go from these parameters to the polynomial expression, if you plug in a final position, you have no clue how that polynomial is going to evolve. It may do something really, really weird. However, if you have something like a speed limit and an acceleration limit, then you can just plug those in directly to these trajectory parameters. The nice part being that we don't really care what the parameterized trajectories do because we know we're going to pick the best one that we can later on at runtime. So the shape of them doesn't matter so much, which is how we ignored position entirely and just cared about velocity and acceleration because those are the quantities that we cared about bounding in the performance of the robot.
Cool. Okay, that makes a lot of sense. Thank you.
Yeah. I'll also have a link to a paper at the end of the talk where we plug this into a reinforcement learning framework. And my student Simon discovered that this parameterization basically works all the time for every robot. So I've used this parameterization for manipulators, and then Simon used it for highway driving, where it's separated into like longitudinal and lateral velocities and accelerations. So
Cool.
in general, for a physical system, these are the quantities you care about.
Thanks.
So what we're trying to handle is this nonlinear, high-dimensional, high-fidelity model. And then also we want to incorporate tracking error into planning. To do this, we'll compute a reachable set just as we saw before. To compute the reachable set for the drone, let me quickly talk about what a zonotope is. So imagine arbitrary dimensional Euclidean space. I'll construct a set Z centered at a point C, where I take the convex combination of C with vectors that we call generators. So what I'm doing is a Minkowski sum or a set addition with each generator, which if I let the coefficients of these generator vectors vary between -1 and 1, it sweeps out this volume that we call a zonotope. This is a special kind of convex symmetrical polytope. And if you're not familiar with it, the rough idea is that you're just adding a bunch of line segments together and sweeping out volume in space. The nice thing is computationally, we can write this thing down as a center plus a generator matrix. So I stitched together my 3 generators in this particular case, times B, a multidimensional interval, which you can think of as the unit hypercube in the dimension of however many generators I have, or you can just think of it as all of these beta I variables stacked together. So we get a super duper compact, computationally efficient representation of a set that is convenient for reachability. The linear map of this object is still a zonotope, so these objects are closed under linear maps. And similarly, they're closed under Minkowski sums. In particular, if I want to add 2 sets together, I can add their centers and concatenate their generators. And then here I've used some MATLAB notation to smush together those coefficients. The core of reachability analysis with these objects is taking my system dynamics, linearizing them, flowing my whole set forward a little bit, and then taking a Minkowski sum with error to dilate for the fact that there's nonlinearity. So with these 2 operations together, I can compute reachable sets. And because when I do either of these operations, I still have a zonotope, it means that I can represent my entire reachable set as a sequence of zonotopes. The way we do this for the drone in particular, I'll show for just a single trajectory parameter, and this should have a star on it. So this K star is the same K here, pardon the typo. The first thing we do is take our time interval. Hopefully you remember from earlier in the talk, we have each trajectory over this little 0 to TF chunk of time. We break it into a bunch of little intervals. And then if there are n of them, we're going to compute n zonotopes. We start with a Z0 initial condition zonotope, and then we apply the following procedure. Oops. Okay. Sorry. Like I said, a little bit untested slides. But anyways, we get a reachable set as this sequence of, in this cartoon version, they're boxes. They're not necessarily boxes in application. The particular toolbox that we used originally to compute these objects is called Cora, and it's available for free as a MATLAB toolbox online. More recently, I've started just doing it myself. So it turns out these linear maps and Minkowski sums and similar operations are not so hard to plug in, but there are existing convenient tools for computing these types of objects. Now, I'll point out that we don't just do this for a single trajectory parameter, but rather a continuum. So we set up our initial condition zonotope in this higher dimensional K cross X space. So parameters cross with workspace. And then we compute a sequence of zonotopes in this high dimensional space, which is a forward reachable set, but just for the planning model in the case of the drone. The nice part is, because of the Minkowski sum property I mentioned earlier, we can now add tracking error to this. Critically, we can also back out a subset of this high dimensional set corresponding to one trajectory, which is a procedure we call slicing. So if this is my decision variable space on the left, I can pick a point and get the small reachable set corresponding to just that trajectory by basically doing a linear operation on the high dimensional zonotope. Okay, before I dive into the tracking error idea, are there any questions about zonotopes or the planning model reachable set? All right. So how do we deal with tracking error?
I guess
And
quick
as a cartoon reminder, oh, go ahead.
Just doing these zonotopes and the linearization and incorporating error compared to the sum of squares thing, how much more conservative does it tend to be? And I assume that the benefit is it's much more scalable.
That's right. So the conservatism is usually, it's hard to say because you can sort of pick a trade-off in complexity versus conservatism with the zonotopes.
Sure.
So like if you have more generators, you can get a more like blob-shaped zonotope initially, and then it will be less conservative but more computationally expensive at runtime, and even offline. So you can, if you do it the simplest way where you just put boxes around everything, it's super duper cheap and it'll be a lot more conservative than the sums of squares version, like a lot more conservative. So picking the generators, how finely you discretize time, or sorry, partition time, because you're still considering the continuous time case. And then the system dimension, all of these parameters are sort of hyperparameters to play with to figure out how conservative you want to be. So
Okay.
in the sums of squares case, the hyperparameters were the polynomial approximation degree and dimension. In the zonotope case, it's the again the dimension, but then the zonotope particular parameters. And there's no clear answer off the top of my head which one's going to be better.
Sure. Okay. Thank you.
So as an encouragement to the students, just try them both. We have code online for both, so you can give them a shot and see what you like. In the tracking error case, we have not figured out a way to solve this with the sums of squares approach at all. It's too high dimensional. Because what we're trying to do right now in this cartoon version is compute the difference between the simplified planning model and the high fidelity model trajectory. And in particular, we want to fit a sequence of zonotopes that over approximate the error between these two trajectories just in the workspace. So I'll denote these error zonotopes EI as a function of my initial velocity, and I'll explain why they're a function of the initial velocity. And we want to compute them to contain our position minus our desired position at each time in each of those short time intervals that we broke up the whole reachable set time into. So the cool part here is by looking at the dynamics of the drone, it turns out that our choice of initial condition, like velocity, is the most important thing in terms of our tracking error. So what we can do is we can prove that if we have linear actuator dynamics, then the worst case tracking error for the high fidelity model is always produced by committing a maximum allowable change in velocity. And if that sounds like it makes sense, good. Basically, I'm going to have more error if I suddenly command 5 meters per second from 0 than if I command 2. That should totally make sense, but we confirmed it, at least formally, somewhat. All right, so this trick then lets us do reachability analysis on the high fidelity model of the robot. What we do is we then take our blue reachable set from the simplified planning model in the dashed line here. And then we can add these two reachable sets together, leveraging that Minkowski sum property you saw earlier to get a, in this case, yellow reachable set that encompasses the fact that I'm not going to track the trajectory perfectly. So my planning model reachable set plus my error reachable set, that's a function of the velocity, contains the robot at each time. Then if this yellow tube lives outside of obstacles, we're golden. All right. So assume that this holds. Yes, we've recently proved why it should hold, but I think the proof needs to be stronger. So if anybody wants to go do some proving, boy, do I have a job for you. And under the reasonable assumption that we can compute a high dimensional reachable set of the tracking error, then we just add that to our simplified reachable set and we're good to go. We have an FRS for this high fidelity model of a drone. In particular, the for reachable set is a sequence of big N zonotopes, where each zonotope is in the workspace X and the parameter space, and then our tracking error zonotopes are just, for the particular case of the drone, 3-dimensional. Man, I should turn off these subtitles. They are not doing well with math words. Okay, so now what we've done is compute an FRS offline for the drone. How do we use it at runtime? We're going to try and take a similar approach as we did for the car. Given an obstacle in the drone's workspace, we'll intersect it with our big for reachable set, and then try and compute the set of unsafe trajectories that we don't want to choose at runtime. To make this a bit easier to understand, I'm just going to look at one of the zonotopes, but recall that the reachable set is a sequence of them. So we have to repeat this procedure for each zonotope. I'll also put a little hat on it to remind you that the tracking error is now baked in. So we're looking at a for reachable set at a particular time interval for the high fidelity model of the robot. We'll also assume that our obstacles are zonotopes, which is not unreasonable because zonotopes can model cubes, boxes, any convex symmetrical polygon. The question then is the intersection between these two objects non-empty? I'll start gathering convenient math and cartoons on the left and then working the math on the right. The first thing we do is recall the definition of the zonotope, where it's a center plus a generator times this interval matrix. Since by assumption our obstacle is also a zonotope, we can basically write it down the exact same way, and then just set these two things equal to each other. So what now I want to know is, do I have some multi-dimensional interval for my for reachable set that causes points in the reachable set to equal any point in the obstacle? Turns out that solving for this BU is pretty much as easy as it looks. And you end up with an interval with some bounds that you can directly compare to the interval that defines the zonotope. Because recall that the zonotope is this image of the interval -1 to 1 mapped through the affine transformation with C and G, putting it out into the robot's workspace. So if I'm thinking about things in the hypercube space, where B and B sub U live, I can actually do this interval intersection super duper easily by just comparing the left and right bounds of each dimension. In other words, we're just intersecting a bunch of cubes. And if they do intersect, then I can immediately identify the set of unsafe trajectory parameters. So what we prove is if there are unsafe parameters, then these intervals, these high dimensional intervals, have non-empty intersection. The convenient part is checking if I live in the unsafe set is equivalent to taking a maximum over a collection of linear constraints. So if you took nothing else away from that, basically by representing the reachable set with a bunch of zonotopes that are high dimensional in the workspace and the parameter space, at the end of the day, I can turn everything into a bunch of linear constraints for an optimization program. What that means is that it can be really fast to evaluate online. So what does it look like at runtime? Oh, go ahead if there's a question.
Does this mean that so we talked about the trade-off of having simpler zonotopes and computational complexity. Does having simpler zonotopes here make the collision checking faster?
That's exactly right. Yeah. And you can think of the number of faces of a zonotope is really what matters. And that number is exponential in the number of generators. So simplifying the zonotopes is super duper important. I haven't worked on this myself, but there's a lot of techniques for what they call ordering, where you're over approximating a zonotope with a new zonotope with fewer generators. And we do apply those techniques sort of in the offline computation.
Cool.
All right, so how do we use this object online? We're always solving the same problem. Optimize our cost over the trajectory parameters subject to being safe. A solution may look something like this, and then we know that the robot should not crash. We assume at time 0, we can just hover in place if we need to. So as long as we start out with something safe, then we can prove that the robot will never crash. All right. Before I get into what it looks like, does anyone have any questions? This is the end of the drone section.
I have one question. I forgot to ask the trajectory. How we find the optimal trajectory parameters? This not necessary to be a convex function, right?
That's exactly right. I don't think I have any slides about it, but anyways, in general, what I've done is use fmincon or IPOPT or a generic nonlinear solver, and then usually just hope that it gets to a feasible solution quickly. The nice part is all of my work has cared entirely about collision avoidance and not about optimality until more recently. So in general, you're right. We're solving a non-convex, nonlinear optimization program, and there's no optimality guarantee that will choose the best trajectory parameter. But we can often find a feasible parameter really, really quickly by descending along the constraint gradients. Does that make sense?
Yes, thanks.
Okay. The nice part is I had a paper come out recently in TRO, which is referenced in the at the end of the talk. We can use a different approach to nonlinear optimization. As long as our cost function is a polynomial, we can provably find the optimal solution really, really fast with parallelization. And that's what we call RTD star. So that one, I should have a video of it somewhere in the later bits of the talk, but the basic idea is that it's like a branch and bound approach over the compact domain of trajectory parameters. And then by representing the cost function as a polynomial, you can provably find the globally minimizing point, so the optimal trajectory parameter. Remind me at the end of the talk, and I'll see if I have the video, or at least I have a link to it. But it's a good question. We have solved it, but we haven't applied that solution to all of the different robots. Okay, so I'll show a simulation first, and then I'll show a never before seen video. But basically, here's the robot flying through a bunch of trees and figuring out how to do that flight on its own. The nice part is over, at this point, thousands of such simulations, the robot has never crashed. All right, so I think I actually do have time for the manipulator stuff because it's super quick. But does anyone have questions about zonotopes, the drone models, or what we're doing about unmodeled aerodynamic effects? Cool. On the manipulator side, I'll just do this entirely with cartoons, basically. But there are more detailed slides available that I can send along later. And you can also check out the paper. So the setup here is I have a robotic arm with an initial condition in purple, a desired goal in gold, and then some obstacle that it has to get around. The idea is, as always, to compute a small reachable set for a parameterized family of trajectories. And that may look like this blob in the robot's configuration space. So here on the left is a cartoon version of all of the joint angles of the robot, Q. As before, what we'll do is we'll take our little tiny forward reachable set, intersect it with the obstacles to identify unsafe choices, and then given a waypoint that we want to reach, which may not necessarily be safe, we'll optimize within our safe set and thereby find a trajectory that goes around the obstacle. So we keep doing this procedure, and eventually we'll get past our obstacle, hopefully, and get to our global goal. The hopefully part is where the optimality question from earlier comes in. And it turns out that by pairing this type of RTD approach with an RRT star or A star dynamics ignoring search, you can basically create the waypoints that will get your robot around obstacles to the goal and then track those waypoints safely with RTD. So the challenges for manipulators are we need this high dimensional planning model. We need to consider all of the joints of the robot. And there's a nonlinear transformation to go from the configuration space to the workspace. So collision checking one configuration is not so bad, but collision checking the continuum of configurations resulting from a trajectory can be pretty tricky. We again take the same tack. We parameterize trajectories, where short trajectories in the joint space end up being short trajectories in the workspace. And the particular parameterization is very similar to what you saw with the drone. We consider the initial velocity of each joint and a commanded acceleration of each joint. Then in the joint space, let's say for the ith joint, a velocity profile might look like this, where it accelerates by the from the initial velocity, it accelerates according to the commanded velocity, and then after our amount of time t plan breaks down to a stop. So like I mentioned earlier, parameterizing velocities and accelerations turns out to be really convenient for every robot we've looked at. However, directly computing a reachable set of such trajectories in the joint space makes it very hard to map those reachable sets to workspace because you have to do a nonlinear transformation. So what we did instead is compute the reachable set in the space of sines and cosines of each joint. So if I pick a trajectory parameter, a single trajectory may look something like this, where it travels along the unit circle for this particular joint shown. And then for the continuum of trajectory parameters, we'll get this arc of the unit circle swept out. And we can call this object the joint reachable set for a single joint. We also represent this as a sequence of zonotopes. So what we end up with is, it's a lot tighter than in the cartoon, but we end up with a thin strip of zonotopes on the unit circle. Now, because we represented the sines and cosines, so the building blocks of the nonlinear transformation from configurations to workspace, we can actually use those to compose a workspace reachable set of the robot. So let's just look at one joint with, let's say, a parameter space K1 and this little joint reachable set that you saw in cartoon form. The first thing we can do is, working in this high dimensional space, we can actually turn these objects into rotation matrices. Since we're holding on to sines and cosines, basically you can just reshape these zonotopes. And then we define what it means to multiply a zonotope by another zonotope, but that ends up producing the workspace volume that we cared about, this cartoon volume in workspace for the first link. So given the volume of this purple link, I can multiply it by some transformation of this sequence of zonotopes to produce the swept volume of that link. The reason this matters is because I care about what portions of the swept volume live outside of obstacles. If I rinse and repeat for the second link, and then the third link, I can produce this swept volume object where I have an initial configuration of the arm with initial velocities, and then for all possible choices of trajectory parameters, I know that the arm is going to live inside the union of these blobs. We call these objects rotatotopes because what we're doing is we're constructing a zonotope of rotation matrices and then multiplying it times a rotated or swept volume. It turns out it's a special case of polynomial zonotopes, and polynomial zonotopes are just like regular zonotopes, but the coefficients are allowed to be polynomials. If that meant nothing to you, don't worry about it. Just remember rotatotopes because it's the most fun word we've come up with in our research so far. All right, so all of this composition, like stacking the reachable set together, actually has to be done online, which is, I think, one of the cooler parts of the manipulator thing, because for all of the wheeled robots and drones, we had to do all the reachability offline. But here, we're creating the reachable set on the fly at runtime with GPU parallelization. Then we basically applied the exact same procedure you saw with the drone to generate those collision avoidance constraints, where we're intersecting high dimensional zonotopes and then projecting the intersection into the parameter space, and then creating a cost function, such as reaching that goal position, and optimizing over the space of trajectory parameters. So given this initial guess, because as one of you noticed, these are non-convex nonlinear programs, so we tend to give them an initial guess. That initial guess may converge to hopefully it'll converge to a feasible solution. And then the corresponding subset of the reachable set in gray is a trajectory that avoids the obstacle while still tending towards the goal. That was the entire cartoon version for the manipulator case, and hopefully it makes sense in the context of the wheeled robot or the drone. But are there any questions? Okay, fun video time. So here what you'll see is this fetch arm trying to get from this low shelf to the high shelf without hitting the shelf itself. The arm is shown, so this is what the robot is seeing. The arm itself is in blue. That gray subset of the reachable set for the current trajectory is in gray. Each intermediate waypoint that the robot is trying to reach is in black. And then the global goal is in green. So given a good set of waypoints, which can be found pretty quickly with, for example, A-star search, the robot can basically do a perfect job and not hit any of these really thin obstacles. The reason I say thin obstacles is because if I were to discretize in time, then it becomes tricky to say that I have avoided collision with a pair of thin obstacles, or sorry, between a pair of discrete times. I could be like just on either side of an obstacle, but actually be in collision between them. So the fact that we're considering continuous time is actually super duper important in this case. The other thing that is nice about this is that we can sit on top of an RRT, a deliberately unsafe RRT, and turn it into a safe RRT. So here what you'll see is the robot trying to go from below the table to above the table. And the RRT that we use to generate waypoints is basically telling it to crash into the table over and over and over. So here you can see these waypoints are all over the place. They're kind of messy. And we're doing as best we can to track them. As soon as the waypoints start to turn good in a little bit, then we track them right over the table. The nice part is we're also not super duper conservative, though I will point out that there's a plotting error here that, or as well as plotting error and camera position that show like different volumes of these reachable sets versus the arm. But the big takeaway is that the arm never crashed into anything over many, many dozens of times trying this out, which is pretty fun to see. And finally, as we saw before, we can handle dynamic obstacles. Here, my research advisor at Michigan bravely volunteered a glass vase that we stuck motion capture dots onto. And the robot pretty quickly decides to go around them. I did speed the video up at the end because it for some reason, just decided to go really slowly towards the goal. But the big takeaway is over many such trials with the vase popping up, we didn't hit anything. Okay, so I'll skip over the comparisons to other methods and focus in on the key questions. But to summarize RTD as a whole from the whole talk, the challenges that we addressed were planning with respect to tracking error, so model mismatch between our planning model and our high fidelity model of the robot. We considered continuous time and space collision avoidance by being clever about how we discretize. And then we developed obstacle representations via discretization or zonotopes that enable fast and in particular real-time trajectory planning with safety guarantees. So if you apply these techniques correctly, then you have provably safe real-time continuous time and space trajectory planning, and you can incorporate tracking error and represent obstacles. So when is this a good method to use? When you have an accurate high fidelity model, a good tracking controller, or a separable or low dimensional planning model. And I think we've touched on where you would get each of these throughout the talk, but turns out that we have those for all three of these robots, except the drone. Sometimes you just have no clue about your dynamics, or you have something very unexpected appear. Or you don't know how to design a tracking controller, like perhaps for a soft robot. Or you have really large model uncertainty that can lead to very high conservatism. When any of these apply, usually what I would do is really try and find a good model or design a good tracking controller, or otherwise reduce the uncertainty. However, ongoing research that I'm working on now at Stanford is how do I directly bake that uncertainty into my reachable set? And that's something maybe you all can think about as well. Everything you've seen up until now deals with bounded model uncertainty, but we haven't considered perception uncertainty or unknown disturbances from outside of the model. So perhaps a world model. But the drone does actually do flips, not with RTD, it's just a fun feature of the drone. All right, and then this is my takes, but what do I think are really hard for RTD and autonomy in general? Perception and perception uncertainty in particular is really, really tricky. I'm only now learning about how to deal with that, and there's no real good answers there. Safe planning for high dimensional, hybrid, and nonlinear models, so the Cassie robot you see at the bottom, and then making real-time guarantees for both perception and planning. Much as we saw on the planning side, on the perception side, there's this trade-off between accuracy and speed. And often you'll see approaches like YOLO or something that are doing one frame at a time, finding whatever's around you, but struggling to enforce consistency over an extended chunk of time. So getting all of the things working together is still really hard. That's still why we don't have autonomous cars everywhere. And I would say that the hardest part of all of these ongoing challenges is going to be incorporating uncertainty in a meaningful way into perception and planning. Hopefully, I don't know if anybody has like strong disagreements with any of these statements. They're pretty banal as far as I'm concerned, but that's been my take. Okay, how should you learn this method? Follow this handy dandy flowchart. If you like math or code, you have options. If you like math, how much detail do you want? If you want lots of detail, then my dissertation, I wrote it as a monograph to be really accessible. It goes into a lot of detail, but it's, as far as I'm concerned, as far as I understand, it's quite accessible. And then if you want just a little bit of detail, we have the 6-page paper from ACC in 2019. You'll get hopefully the PDF of these slides, so you can just click the links. On the other hand, if you like code, well, then what robot do you want to play with? You have 3 choices: cars, drones, and arms. In either case, in any of these cases, we have a simple repository and then a more complex repository. Except for the arm, you're just going to get all of it in one shot. And more recently, we've done work with safe reinforcement learning, where RTD sits on top of a reinforcement learning agent as this sort of safety layer. So we have that online as well. This work has been funded by very generous funding agencies and has led to a ton of open source code. So please go check it out. I'll also mention from the earlier question, we have this glob opt Bernstein. So it's called a Bernstein algorithm that comes with optimality guarantees for RTD. If you have a GPU, then you can actually run it on board the robot really fast. And then there's a whole bunch of papers about this, not in any particular order, but yeah, feel free to check them out and email me with questions or concerns. Happy to take any questions now as well.
Okay, thank you, Shreyas. I know that we're a little over time, so if people need to leave, please go ahead. And if you have questions, it sounds like Shreyas is willing to stay a little bit. Otherwise,
yeah,
I'll
sorry
see you
about
on
the time thing.
No problem. While people are sorting things out, I have a question. So we've talked a little bit in class about safe learning and learning safety. So like safe learning, kind of what you just hinted at of like trying to form the safety layer around your reinforcement learning. For learning safety, you mentioned, when you find out that there are unmodeled effects, if you could somehow learn the model of them, are you able to update your analysis, or do you need to, turn off the experiment, go recompute things, and then do it again?
It's unpublished, and I was supposed to submit a paper about it, but yes, in short, yes, we can update in the case of the drones in particular. So let me find the backup slide here. I'll just walk through this pretty quickly because I think it's quite tidy. When we're talking about Zonotope style reachable sets, we saw that linear maps and Minkowski sums were really efficient and everything stays as a Zonotope. By efficient, I mean that you're either adding vectors or concatenating vectors. So you can do it really, really quickly. So this tracking error reachability thing is, we did it offline, but you could continue to update your representation of the tracking error zonotopes online.
Cool.
The reason being, we're basically over approximating our space of possible velocities with the zonotope. And then if that I write down as an interval, I can just look at the corners of that interval. And then what we do is we basically sample and collect. So I'm not going to explain these in much detail, sorry, but the rough idea is we're sampling velocities offline to compute a reachable set for the high dimensional model of the drone.
Mm-hmm.
And then when you're flying the drone, you're still just sampling velocities. So you can continue to update the error representation of your robot as you fly.
Cool.
In our particular case, we represented it as a lookup table. So it's like super fast to both update and reference. But you could learn a function via support vector machine or neural network, whatever you wanted, that spits out a sequence of zonotopes. I don't know, it'll depend on the architecture if you can actually backpropagate through it in real time. But the learning for safety side means, at least in my understanding, it means computing this reachable set and updating it on the fly. And that's totally doable with the current code. Yeah, unfortunately, that was right when I moved to Stanford, so I just had to drop that project. So if anyone wants to do it, go for it.
Other questions?
I had a question regarding the manipulator stuff.
Mm-hmm.
So a lot of your work seems to focus a lot on object avoidance and stuff. So in regard to like actually interacting with objects, do you have any thoughts on like how to kind of deal with changing dynamics when you interact with objects, or maybe even cases where you don't necessarily want to avoid certain things, but like, for example, a curtain you can like pass through to some degree before it becomes unsafe. Yep. Thoughts on things like that?
That's a good question. So in terms of the changing dynamics, like suppose I picked up something really heavy. We are writing a paper about that right now. So the idea is to change the way we compute the reachable set to incorporate uncertain model parameters and the dynamics of the robot, no longer just the kinematics. I don't have much more detail for you in terms of an answer other than that we're basically computing the reachable set with the mass matrix and like an uncertain mass matrix for the manipulator in the loop. This is the hand motion for in the loop, apparently. And on the side of actually interacting with stuff, I think it's a super interesting question. I got the same question on the quad order side of like, how do I use this to perch on stuff? It turns out with a zonotope representation, let me find a sufficiently accurate cartoon here. All right, so suppose that I'm looking at I've mapped these pink blobs to my parameter space. We can also inner approximate these by basically a scaling of the intersection, and then optimize to be inside of the zonotope instead of outside of it, which is great because it's also convex. So you can provably optimally find in the quad order case, you could find the trajectory that goes in perches or like guarantees you to interact with an object. And then your cost function could express something like how fast you hit it, right? So that's one way to solve it. On the soft object side, like a curtain, I would say we just wouldn't worry about it. Like we would just not model it. You could just construct a cost that made the arm go from left to right near the curtain and not model the curtain at all. That seems like the easiest. If you know something semantically, so like if your perception system tells you, hey, I don't even care about this thing, it's not a real obstacle, then if you never hand RTD an obstacle, it won't care about it. The tricky part is like, what happens if I like pick up a pool tube or something squishy and foamy? It's hard to do. It's hard to model. If you can generate reliable predictions of what will happen when that object is interacted with, which Dmitry Berenson at University of Michigan has a lot of work on that. But if you can model with some fidelity what's going to happen to the soft object, then you can start to incorporate that into the cost function. It'll be harder to incorporate into the collision avoidance constraints. So for example, like, I want to pluck a string without breaking it or without missing it? That's gonna be really hard. And I think it's an interesting question. Hopefully that gives you a feel.
Yeah, thanks.
Oh, I just found the clock that tells me what time it is. All right.
Any other questions, or is everybody just hanging out because we have nothing else to do besides Zoom?
Oh, I have some
Aren't you grad
technical questions.
students? Okay, go ahead.
Sorry. I was wondering, like, when we're talking about high fidelity model, and we're trying to find a track error bound over the G function. So what if the high fidelity model is not very good, and how we do that to finding a good bound for that?
We've actually had to deal with.
Conservative, I mean, yeah.
That's a really good question. And it's something we had to deal with in the case of the electric vehicle. So this thing, our high fidelity model wasn't accurate all the time. It was accurate within 10 centimeters all the time. So we found from data from driving around in a place without obstacles that our high fidelity model was 10 centimeters accurate. And we buffered every obstacle by that additional 10 centimeters, which kept us out of collision. And I can promise you we didn't crash at all. But ideally, what I think would be really cool would be to directly compute the forward reachable set for the high fidelity model and be able to somehow do that fast enough where as you improve the model, you can reduce the size of, for example, an uncertain parameter set. So that's exactly what we're doing for the manipulator that's not published yet. We say, okay, my mass matrix is uncertain, but I can compute a forward reachable set for the manipulator with an uncertain high fidelity model. And it's just gonna be a little bit big. It'll be a little conservative. And then as I move around, I can hopefully in real time recompute the forward reachable set with a smaller uncertain bound on my parameters. The way I've implemented that specifically here at Stanford is for the drone case, where we're running what we call a zonotope Kalman filter. So just like regular Kalman filtering, but instead of updating a point estimate of your state, you're updating a set estimate represented as a zonotope. So you're, and I can send a link to that talk, but one way to basically do it is to say, okay, I know I have model uncertainty. Let me just keep recomputing the reachable set at runtime and then use a Kalman filter or some other filtering technique to continually improve my model as I get more data. None of this requires any learning, and I think it's quite related, or none of it requires any machine learning, which is nice and is quite related to Sylvia's question earlier of, how do you learn for safety? All of this stuff is just updating set representations of the robot. The next frontier then is how do you do this with machine learning techniques and still hold on to any guarantees? I don't know.
Shreyas, I have to get going to my next, but if I make you co-host and if you still have time and people still have questions, you can keep on going. But thank you so much and let's catch up. Oh, you also have to go.
Yeah, okay. I just realized I have a lab meeting. All right, sorry everybody, but please email me with questions.
Okay, yeah, let's follow up with that. Okay, bye everyone.
Thanks for the chance to chat. All right, bye everybody.
Thank you.